let's start with the 21st example, that is the first question from physics part 1. In a muonic atom, a muon of mass the muon is having a mass equal to 200 times of mass of electron, while the charge on muon is same as that of the electron, that is minus e, is bound to a proton. The wavelength of its Balmer series is in the range. So Balmer series means from any higher orbit to second. When electron jumps from any higher orbit to second, then that is the Balmer series. Okay, now let's see. Now we know that in a normal hydrogen atom, the wavelength range is given by r in bracket 1 upon, for Balmer it will be 1 upon 2 square minus 1 upon any higher orbit square. But as we know very well, the Rydberg constant for a hydrogen atom having electron is something else. Okay, r, and here I should take this as r dash, as the Rydberg constant directly proportional to mass. So therefore I can write for this given item it will be 2200 times of r, because mass is 200 times, and in Rydberg constant mass it depends on mass of the moving particle, that's why 200 r in bracket 1 upon 4 minus 1 upon n square. So 1 upon lambda will be equal to 200 into r. Say the transition is from infinite to fourth orbit to second orbit. So lambda will be equal to 200 r upon 4. So it will be 50 r 1 upon lambda. So lambda will be equal to reciprocal of 50 r. Already the reciprocal of r is learned to us, that is 1 by r is 916 angstrom. So this will be 916. So it will be 91.6 upon 5. So that comes out to be 5 ones and then 5 18.2 angstrom something. While this particular wavelength range is microwaves, they have very large wavelength, gamma have very short wavelength, so obviously the range appears in X-rays. So the correct answer to this question is A. Thank you.